So, hi, today we're presenting our course project, which is called Risk-Calibrated Time-Aware Transformers for Distributed System Logs. The big picture is that we wanted to move beyond just predicting the next log event and instead build a system that can help quantify uncertainty in a way that is useful for operations.
So modern distributed systems generate pretty enormous streams of event logs. These logs are both sequential and irregularly timed. A lot of existing work, including the hubs available in DeepLog and Logbird, already treat log modeling as a sequence learning problem and use next level event prediction as a core primitive. In a real operational setting, raw prediction accuracy isn't enough. If a model makes a false positive, overconfident wrong alert, it creates alert fatigue and the user wastes their attention. If it makes an overconfident wrong alert, a false negative, it hides a genuine emergency. So our core thesis is that next event prediction for logs shouldn't be treated as a generic sequence modeling task, but as a risk calibrated decision interface. Not just guessing what happens next. We want to communicate when the model's confident enough to automate and when it should back off.
Yeah.
So here we have four main ML challenges. The first, irregular timing matters. In system logs, same event token can mean different things depending on the time gap that preceded it. Second, we have long-range dependencies, so a failure or a retry cascade again and again can depend on context set that many steps earlier. Short-term memory baselines will usually miss important structure. And then extreme class imbalance and rare events. Most log transitions are routine, but the rare error transitions are the ones that are critical, that we care about. And of course, there's a temporal distribution shift. Even if a model looks calibrated on yesterday's logs, if the exchangeability consumptions break, it won't work on tomorrow. So these are the issues that make it basically a much harder problem than one that requires off-the-shelf text modeling.
Yeah, so our problem formulation, so we model each system run as a variable length sequence of tuples where each element has an event type, a time gap, and optional context. So the prefix we observe is xt. Our primary supervised task is next event prediction, meaning that the target is the next event type. But crucially, our output should not just be top one prediction. We want to model the probability distribution of the next event type, and then use this probability distribution which should be calibrated to utilize to give us some confidence scores. And then we want to create a conformal prediction set, which should include the real, like the correct event type with some marginal probability. So our framing is predict the next event and then turn this prediction into some decision support for operations. Our methodology is a four-stage pipeline. So first we need to construct the sequences. So we need to parse the logs and model the time gaps and event IDs. Then we utilize some representation learning where we embed the information. So we have one embedding of the event type, one embedding of the time distance, one embedding of the context, and one embedding of the positional encoding. And then we train a small causal transformer, and we train this via class-weighted cross entropy, which is because of the class imbalance, which Zach talked about. And we compare this to LSTM and Markov baseline models. Then we have some uncertainty wrapper over our learned model, which will help with operations. So how we calibrate the model is using temperature scaling, where we try to fit some big T, bigger than 0, to calibrate the model to represent real probabilities. And then we use the split conformal prediction to create our prediction sets. And operational translation is that if the set size is 1, then the model is confident and we should automate the response. If the set size is bigger than 1, model is uncertain and we should escalate.
So in evaluation, we have two regimes. First, the controlled synthetic benchmark, where we isolate the properties we care about, long-range dependence, timing sensitivity, rare event shift, the works. As a benchmark, we're not intending this to replace the real data. We're just intending to test whether the implementation expresses the mechanisms we say it should. And the second regime is the real-world HDFS dataset that we retrieved off of LogHub. So we work with hundreds of thousands of block sequences and use chronological training, validation, calibration, test splits to better match the deployment. And we evaluate both general next event prediction over all windows and anomaly triage on the last window only in the real data set. So here we're kind of bridging the theory and the real data. The reason that we kept the synthetic suite is it isolates the intended mechanisms, as we just explained, before the real world noise kind of makes the interpretation messy. In the context long range case, first token determines the correct next event, while the last token before the target is identical across classes. In that setting, the transformer with time reaches perfect accuracy and beats Markov by a full point, which pretty much demonstrates that long-range accuracy matters beyond local transitions. But in the timing matters case, the token's prefix is identical, and only the final time gap changes. So here, adding explicit time features improves accuracy by about 0.427, which is what we would hope to see if timing is actually informative and kind of influential. In the rare shift case, the transformer with time reaches perfect rare event accuracy in the controlled setting, which is as a dummy case. So basically, after we repair our synthetic suite, we were able to pass all 4 core checks. So the implementation works end to end, basically.
Yeah. So here are our first results on the real data, HDFS data. So we see that both the transformers and the LSTM model has higher accuracy than the Markov model, but we also see that the precision and recall is not quite as high as we wanted to. This might be also a symptom of the class imbalance that we have talked about. We also see that there's limited benefit of having time on this data set, which might be because the log sequences are highly predictable already. So one of a notable thing is that the temperature scaling seems to be close to 1, the t equals 1, which would mean that we don't really need the calibration. It's already quite calibrated, which we see from the EC as well. EC, yeah. So now onto the conformal triage. We see that this is a test only on the last window, which might present some label shift compared to how it was trained, which was on all windows. So we see here that the coverage on all the methods dropped to significantly from the 0.9 target coverage. But another notable thing is that the LSTM model seem to have the wanted property of not escalating on normal logs. We see that it only escalates on 3% of normal logs, but still escalates on 35% of anomalous logs, which we will investigate further later.
And here we're kind of focusing on a different evaluation regime. We're looking at the all window conformal behavior, not only the last window anomaly triage, which is basically why the coverage numbers here look much closer to the nominal target. The key point is, as we say, coverage alone is not enough. Markov gets the highest conformal coverage at about 0.972, but it does so by returning much larger prediction sets with the average set size well above 1 at 1.58. The neural models, by contrast, all stay very close to the 0.9 target, while keeping prediction sets much smaller, around 0.94 to 0.96, below 1. So this is what we're talking about. We talk about operator-facing standoff, operator-facing trade-off. Do you want higher nominal coverage at the cost of much less selectivity, or do you want compact prediction sets that are still close to the target? In that sense, the neural models are actually behaving usefully. Okay.
So investigating the LSTM model, here we see a concrete graph of the normal contrasted with the anomalous sequences. And we see that the normal sequences almost always have the one prediction set of size 1, while the anomalous might have 2 and 3. So it escalates on those only. And also we see that the automation precision for the LSTM model is much higher, which we also think is because the LSTM model performs better under label shift, because it compacts the context much better than the transformer in our training case. I think, yeah.
Okay, this is probably the most honest summary slide we've got. What works is the end-to-end HDFS pipeline runs successfully. All learned models beat Markov on prediction quality, and neural conformal coverage stays around the 0.9 target in the all-window regime with compact prediction sets. So the pipeline's real, and it's learning useful event structure, but a couple things don't really work very well. Rare event accuracy is still very low for the HDFS models. Anomaly F1 is also very low for the neural models, and temporal scaling really didn't help. In fact, the expected calibration errors were slightly worse for all 3 neural models after the calibration, chalk it up to entropy, but we haven't ultimately done enough training to corroborate or to optimize, we suspect. So basically, the project, our work succeeds at calibrated sequence modeling more than it succeeds at rare event or anomaly performance. Not what we hope for, but it's informative.
Yeah. So interpreting the findings, we also see that the time doesn't really matter on the HDFS accuracy. Takeaway is that timing value might lie in anomaly prediction and not the average case prediction. Conformal coverage drop, like we said, it might be because of the label shift, which ruins the exchangeability assumptions. And also the way we split the data temporally might also have an effect on exchangeability assumptions. Yeah. Thank you. For future work, we want to maybe look into different conformal methods, increase the the evaluation suite to more complex data sets, and maybe work a bit more on the modeling side and align our objectives better. Yeah, thank you.
Yeah, with great computational power comes great computational responsibility.
Yeah.